Okay, before we go into the contents of this lecture, let's quickly review what we have covered so far in the last, especially in the last lecture. We looked at the relationships between different types of frequencies, capital F, which we have denoted for the frequency of a continuous time signal, frequency FD, a frequency representing for the discrete time signal, and the sampling frequency Fs, which is measured by samples per second. And we have seen the relationship is Fd is equal to F over Fs. Then we looked at the concept of aliasing and why does that happen and how to avoid aliasing, what is Nyquist criteria and sampling theorem. So topics related to sampling have been covered in the last lecture. And the associated readings and examples, I'm sure you must have also covered by now. In today's lecture, we will be looking at quantization and its related topics such as resolution. We will also do some numerical exercises to better understand the topic. Also, we will look at the analog to digital conversion process as a whole. So far we have looked at sampling separately, and we will begin this lecture by looking at quantization separately. But towards the end of this lecture, we will combine both processes and try to look at the overall picture of the analog to digital conversion processes. Right, so we have seen this slide earlier as well, and we are reviewing this again so that we can clearly see what we will be covering in this lecture. We have seen that quantization is a process to convert a discrete time continuous valued signal into a discrete time discrete valued signal, and the output is generated more like a bit stream in the form of bits. So in an analog digital conversion, once an analog signal goes through a sampler and is converted into a discrete time signal representing here as xn, then we discretize the y-axis, we discretize the values of the signal into a finite number of levels, and this process is called quantization. And the signal which goes through a quantizer is called a quantized signal, and a coder then, according to the levels of the signal values, assign certain bits to that sample, converting the discrete time signal into a digital signal, and the number of bits per sample depends on the number of levels we are going to choose for our quantizer. So in today's topic, we will be looking at this area in the initial half, and in the last half of the lecture, we will be looking at the analog to digital conversion process as a whole. Okay, so the quantization definition is given as the process of converting a discrete time continuous valued signal into a digital signal DT/dV, discrete time discrete valued, by expressing each sample value as a finite number of digits. So instead of having an infinite possibility of values, we now have finite number of possibilities within which a signal value can acquire a value from, and this process is called quantization. Alright, so we will spend a bit of time on this slide because I think this slide will help us look at all the topics of interest which are considered under quantization. As we have seen that we start by sampling an analog signal, a continuous time signal. So this signal, which is just starting nearby 0.3 and then goes a bit down and then it goes up again before reaching its peak value at 0.640. This is our analog signal. This is what we call a continuous time, continuous valued signal. And then the first process of analog to digital conversion is sampling. So if in this example we have chosen TS as the sampling period, then the first sample will be taken at 0.0 and the value of that sample, which is represented here by a red circle, is close to 0.283. So the value of that sample will be 0.283 and represented by a circle, red circle here. But then the second sample will be taken after a period of TS seconds and its value is 0.155. And the third sample is taken as 2 times TS and the value is 0.120. And the fourth value is taken at 3 times TS and its value is 0.197. The fifth value is taken at 4 times TS, and then the sixth value is 5 times TS, and so on. This process goes on, and this row represents the values of the sample signals xn in a continuous valued mode. So these values have not yet been quantized. Okay, so once this process is done, then we will go into the quantizer. Okay, if we look at the minimum and the maximum values which this signal can acquire, then this is given that the minimum is 0.0. So this signal can go as low as 0.0 and there is no chance that it takes a negative value. So this is defined as the x minima. X minimum is equal to 0.0, which is this line, and the maximum value which this signal can achieve is defined as 0.7, which is the highest level, and the signal, we assume, cannot go beyond this point. Now this is if you are given, for example, a sinusoid, for example sine 2 pi 50 t. So by looking at the expression, you know that the maximum value of a sine wave can be 1 and the minimum value of a sine wave can be -1. So if you are given that signal, then obviously you will say that, okay, my x minima will be -1 and my x maximum will be +1, because a sine wave can only move between -1 and +1. So in this example, this is not a sine wave, this is an arbitrary signal, and we are told that the minimum value it can have is 0.0 and the maximum value it can have is 0.7. So this difference between the x